America, and we actually are sort of a hybrid of a technology developer and a project developer. So I'm going to want to do this. So we are kind of viewing ourselves as a super developer. We're interested in basically, our mission is to get as much carbon captured as possible, as soon as possible, as much as possible. And we think driving the cost down, as most everybody in the room would agree, is pretty key to that. It's this vertical integration aspect that we're bringing to bear, which is the aspect of we're actually, since we started as a technology developer, we think there's cost savings in actually vertically integrating or kind of doing technologies that we've developed ourselves, although we're not locked in on that, and basically bring this end-to-end value chain aspect. We've got a strong financial department that we're building as well. So teams and whatever, so let me switch over to the technology since this is a tech talk and they asked us to talk about our technology. So this is where we got started in carbon capture, was this frost CC process. So it's a cryogenic carbon capture process. The key strategy in a cryogenic carbon capture process is to cool your flue gas down to the point where the carbon dioxide actually frosts or changes phase from gas to solid, and then it's a relatively straightforward process to separate the solid from the gas. We then liquefy the solid and pressurize it so we can deliver it in typical conditions. So it's not a sorbent process, it's purely a thermophysical process of phase change. So the diagram over here is trying to show the basic idea. We basically take the flue gas, we'll cool it further from where it normally would go up the stack to near ambient conditions. Then we compress it up, and then we reject heat again. So when you compress it, you're doing work, and this is actually the key part of essentially the refrigeration process that you have. It's a Brayton refrigeration cycle fuel, gas phase compression and gas phase expansion. So we compressed it up, we rejected heat again, and then basically we do a recuperation process. We're going to have to cool the flue gas down to maybe 100 or 120 degrees Celsius below zero, and we don't need to leave the product there, so we recover that cold of both the nitrogen, if you consider the rest of the flue gas is mostly nitrogen, and the CO2 doesn't need to stay that cold, and we recuperate it. So we've compressed it, we cooled it near ambient, we've recuperated and get it down near minus 70 degrees C. We start, or maybe minus 90 degrees C, we're getting a lot of the carbon dioxide that's frosting in that heat exchanger. And then the key last aspect is you expand it, you do that work, and it's not just simply a throttling valve, you actually have to pull the work out of the gas, so actually have it run through a turbine, and in that process you basically get to pull, it lowers the enthalpy of the gas, and that's essentially the cooling process. So, and then of course we can separate the solids and then we come back and recuperate. So that's the broad idea. We think it works well with all the typical flue gases from coal and SMR processes that are relatively high concentration all the way down to the natural gas type combustion processes as well. Of course, it also works, as we've talked about in the meeting today, cement and steel and other industry applications we think were quite attractive there as well. So this chart is trying to illustrate why we're excited about this, is the fact that we're kind of this curve, we're this point here, we've got we think the total capture cost might be down in the $20 a ton range, and again, in the spirit of trying to keep the 5 minutes, the charts on the right are kind of typical amine capture today, sort of a Petronova type example. Overlaid on this is, we think, we worked for a long time in the energy storage space, and the price of wholesale capacity and electricity in North America is quite low. So we're actually using the cost of energy and capacity in the United States, actually what you would have to pay to capture, which is a little different framework than how the DOE and others use it, but it's sort of what you would have to pay power plant companies to put this in. I should have mentioned that this is a very add-on system. We have minimal interaction with the plant aside from we take their flue gas, we put it through our system, and we take electricity from the plant. So we don't have to integrate into the thermal power systems. And so if you look at these curves, you kind of see that the top parts are the energy, capacity, and O&M costs, and they're all relatively similar. That middle point is just simply where we think the amine guys, if they could get 40% of their capital cost out, they would get quite a bit better. And the key point is that bottom chunk is the capital cost. So that's our key driver, is lower the capital cost. And then why this is an exciting business case is if you're going to get paid somewhere up in this range for 45Q and your costs are down here, you have a super attractive project. So this, when 45Q came along, we said, we want to be in this business. And rather than try and convince the power companies to buy our equipment, we just want to own and operate these projects. So that's the key aspect. And that's how it circles back to our final, basically we've switched, let's go bring projects to bear. So we had that, and then we said, what about ethanol? That's a relatively straightforward. There's no technology development that we're still working on Frost CC, so we're basically go bring these pieces together, and a lot of what's been talked about in this meeting today. So phase one is actually go deploy with ethanol. We've got some low-cost compressors that we're invoking there and what have you, and then I want to just point out that although we have proprietary technologies, we're actually just trying to do projects with the most cost-effective solutions. So for all the other technology guys, come talk to us. We're happy to try and get projects done together. Thank you.